To the heart of scientific understanding often requires us to venture beyond the familiar. For centuries, mathematicians grappled with equations that seemingly had no solutions. Equations that demanded the square root of a negative number. The solution? Inventing a new number, one that defied conventional wisdom. This radical concept, the square root of -1 denoted by the letter I, unlocked a new dimension in mathematics. No longer confined to the linear world of positive and negative, mathematicians could now explore a plane of numbers where the real and the imaginary coexisted. Complex numbers, born from intellectual daring, hold the key to unlocking some of the universe's most closely guarded secrets. From the ethereal dance of quantum particles to the flow of electricity that powers our modern world, complex numbers are not just present, they are essential. A complex number at its heart is a simple concept dressed in intriguing attire. Imagine a number with two distinct parts, a real part and an imaginary part. The real part, as its name suggests, resides on the familiar number line, encompassing all the numbers we encounter in our daily lives. The imaginary part, however, ventures into the realm of the imaginary unit, denoted by I, which is simply the square root of -1. A complex number is often represented as a plus by, where A represents the real part, and B represents the imaginary part. Think of it as a tag team, a duo working in tandem to represent a single entity. This unique combination of real and imaginary components grants complex numbers remarkable properties. Visualizing complex numbers is key to understanding their power. While we can easily picture real numbers on a number line, complex numbers, with their two components, require a two-dimensional playground. This playground is the complex plane, a Cartesian coordinate system where the horizontal axis represents the real part and the vertical axis represents the imaginary part. Each complex number finds its unique place on this plane as a point, its coordinates defined by its real and imaginary components. The complex plane is not merely a static map, it's a dynamic stage where complex numbers can rotate, stretch, and interact. This geometric interpretation enriches our understanding, transforming seemingly abstract mathematical operations into elegant visual transformations. The real power of complex numbers shines through in their ability to simplify complex problems, particularly in physics. One such area is the analysis of two-dimensional motion and vector quantities. Vectors, which possess both magnitude and direction, are fundamental to describing physical quantities like velocity, force, and displacement. Representing these vectors on the complex plane using complex numbers allows us to leverage the elegance of complex arithmetic. Adding or subtracting vectors, which can be cumbersome with traditional component-wise methods, becomes as simple as adding or subtracting complex numbers. Furthermore, rotations, crucial in analyzing circular motion, or the behavior of rotating systems, are elegantly handled by complex number multiplication. This elegant representation simplifies calculations and provides a more intuitive understanding of vector transformations. Venturing further into the realm of physics, we encounter complex numbers playing a pivotal role in electrical engineering, specifically in the analysis of alternating current circuits. AC circuits, characterized by the cyclical reversal of current flow, are the backbone of our modern power grids. Analyzing these circuits involves dealing with components like resistors, capacitors, and inductors, each responding differently to the fluctuating current and voltage. Here, complex numbers come to the rescue through the concept of impedance. Impedance, a measure of a circuit's opposition to the flow of AC current, encompasses both resistance, opposition to current flow, and reactance, opposition to changes in current or voltage. Representing impedance as a complex number elegantly captures both these aspects. This representation allows engineers to analyze AC circuits using the same mathematical tools used for DC circuits, simplifying calculations and providing a unified framework for circuit analysis. Perhaps the most profound application of complex numbers lies in the heart of modern physics, quantum mechanics. Quantum mechanics, the theory describing the behavior of matter at the atomic and subatomic levels, reveals a reality far stranger than our everyday experience. Here, particles behave like waves and certainty gives way to probability. In this strange and counterintuitive world, complex numbers are not merely convenient mathematical tools, they are woven into the very fabric of reality. The wave function, a mathematical entity describing the quantum state of a particle, is inherently complex valued. It is the square of the magnitude of this complex wave function that dictates the probability of finding a particle in a particular state. In the quantum realm, complex numbers cease to be mere mathematical constructs. They become the language in which the universe whispers its secrets. Beyond the microscopic world of quantum mechanics, complex numbers find practical applications in controlling and understanding dynamic systems. Control theory, a field with applications ranging from robotics to aircraft design to economic modeling, relies heavily on complex numbers to analyze and predict the behavior of systems over time. The response of a system to external inputs, crucial in designing stable and efficient systems, can be elegantly represented using complex numbers. The poles and zeros of a system's transfer function, which dictate its stability and response characteristics, are often complex valued. Analyzing these complex poles and zeros provides engineers with invaluable insights into the system's behavior, allowing them to design controllers that ensure stability, optimize performance, and achieve desired outcomes. Despite their ubiquity and power, complex numbers are often shrouded in an air of mystery and misconception. The term imaginary, while historically rooted in the initial skepticism surrounding their existence, can be misleading. Complex numbers are no less real than their real counterparts. They simply exist in a different dimension of mathematical thought. The beauty of complex numbers lies in their ability to unify seemingly disparate concepts, providing a powerful and elegant framework for understanding the universe around us. From quantum mechanics to practical applications in electrical engineering and control theory, complex numbers are not merely abstract mathematical entities. They are the language of nature. They reveal the hidden patterns and underlying principles governing our reality, driving advancements in our understanding of the cosmos and our place within it.